Imagine a grandfather clock, but one that never needs winding, one that doesn't even have gears. Instead, its tick-tock is a fundamental rhythm, a pulse that's woven into the very fabric of its substance.
And that rhythm persists indefinitely, locked in, without consuming energy to maintain the oscillation. It's a perpetual, ordered motion in time.
It sounds impossible, but physicists call this state of matter a time crystal, and for the first time, they've just managed to connect one to our world.
Right. A team of researchers, primarily at Aalto University in Finland, published a paper in Nature Communications showing they successfully coupled a time crystal to a tangible mechanical device.
Okay, Arjun, before we dive into what they did, we have to start there. What exactly is a time crystal? It's a term that fires up the imagination.
It really does. The concept was first proposed by Nobel laureate Frank Wilczek back in 2012. The simplest analogy is with a normal crystal, like a diamond or a salt grain. In a regular crystal, you have atoms arranged in a repeating pattern in space. It's a spatial order. A time crystal has a structure that repeats in time.
So its lowest energy state, its default state, isn't static, it's in motion, it's oscillating?
Precisely. It's a non-equilibrium phase of matter. It spontaneously breaks time translation symmetry. In simple terms, the system has a built-in clock, a natural frequency that it prefers to tick at, which is different from any external push you might give it.
That's the part that's hard to grasp. It's not a perpetual motion machine, right? It doesn't break the laws of physics?
It doesn't. You can't extract limitless energy from it. Think of it more like a perfectly balanced, frictionless pendulum that's been set in motion in a quantum system. Its tick is incredibly robust and stable because it's a property of the whole system acting in concert.
Okay, so it's this self-sustaining rhythmic state of matter. How did the scientists at Aalto actually make one for this experiment?
They used a really elegant system. They took a sample of superfluid helium-3, a rare isotope of helium, and cooled it down to within 1/10,000th of a degree of absolute zero, just fantastically cold.
So almost as cold as it's possible to get. Why that material?
Because at those temperatures, helium-3 becomes a superfluid, and you can create quasi-particles called magnons within it. A magnon isn't a real particle like an electron, but a collective excitation of the spins of atoms, like a wave traveling through a crowd doing the wave at a stadium.
A spin wave. I like that.
The researchers, led by first author Jerry Makinen, corralled these magnons together. They created so many that the magnons formed a Bose-Einstein condensate. That's another exotic quantum state where all these quasi-particles lose their individual identities and start acting as a single, unified quantum object.
And that condensate of magnons, that's the time crystal.
Exactly. This single macroscopic quantum object began to oscillate spontaneously and coherently in time. It had a persistent, rhythmic magnetic field. They had created a continuous time crystal.
Wow. Okay, so that's the first half of the story. The incredible part of this news is that they didn't just observe it in isolation, they connected it.
Yes, and that is the real breakthrough here. It's the difference between discovering a new kind of energy source and actually building the first wire to tap into it.
So what was the wire? What did they connect this quantum tick to?
They connected it to a mechanical resonator. You can picture it as a microscopic drumhead, a tiny vibrating plate made of silicon. This resonator was placed very close to the time crystal. And because the time crystal was putting out an oscillating magnetic field, that field exerted a tiny rhythmic force on the silicon resonator.
And the resonator started to vibrate?
It started to vibrate. And here's the crucial part. It vibrated at the exact same frequency as the time crystal's tick. The rhythm was transferred from the exotic quantum world of magnons into the tangible classical world of a vibrating object.
So the quantum metronome was now physically tapping on a drum. They created a bridge.
That's a perfect way to put it. The paper describes it as a cavity optomechanics-like platform. In optomechanics, you use light to push a mechanical object, and the object's movement changes the light. Here, they use the time crystal's magnetic field to push the mechanical object.
This feels incredibly important. Is this the first time we've been able to read out the state of a quantum crystal in this way?
Essentially, yes. By measuring the vibration of the silicon plate, which is something we know how to do very well with conventional tools like lasers, they could know with certainty what the time crystal was doing. It proves we can extract information from the time crystal and interface it with other systems. It turns it from a laboratory curiosity into a potential component.
A component for what? That's always the next question. The university's announcement mentioned quantum computers.
That's the long-term vision. The key property of this time crystal's oscillation is its robustness. It's topologically protected, meaning it's very insensitive to small fluctuations in the environment. It just wants to tick at its own specific frequency no matter what.
Which is the opposite of most quantum systems, right? Qubits are notoriously fragile and easily disturbed.
Exactly. So you can imagine using a time crystal as an ultra-stable clock to synchronize operations inside a quantum computer. Or perhaps even as a very stable form of quantum memory where the tick represents a stored piece of information. And the coupling works both ways. If you can make the time crystal move the resonator, you can also use the resonator to influence the time crystal. This opens the door to creating highly sensitive sensors.
So, to be clear, we are not about to get time crystal-powered laptops next year. This is still very, very early.
Extremely early. Remember, this whole system is inside a cryostat at a fraction of a degree above absolute zero. It's a massive, complex laboratory setup. But it's a Wright brothers moment. It's a proof of principle. They show that this exotic phase of matter can be harnessed, that it can do work on a classical object, and that its state can be read. It's no longer in a world of its own.
There's something really beautiful about that. We always talk about the strange divide between the quantum world with its fuzzy probabilities and our classical world of solid, definite things. This experiment put a foot across that divide.
It really did. It physically linked them. The same rhythm played out in both realms simultaneously. It showed that the bizarre rules of quantum mechanics can produce something with the stability and predictability we expect from a classical clock.
It's a new kind of order in the universe that we're just learning to hear the rhythm of.
And now we've built a device that can listen.
So if there's one thing to take away from this, what is it?
I think it is that we found a new tool for the quantum toolbox. By successfully coupling a time crystal to a mechanical device, scientists have shown that these strange, rhythmic states of matter aren't just theoretical oddities. They are potentially controllable, readable, and useful components for the next generation of technology.
A new tool and a new bridge between worlds. A truly beautiful discovery.